Hello and welcome to this video on logistic regression. This is the first part of a two-part series in which I'll try to first explain what this thing is, and in the second part we will be building one from scratch. We'll be building a binary classifier that would use this model, and we'll be working on the iris dataset. This dataset is a good starters or a beginner's dataset for classification tasks because of its simplicity and because there's only 4 features involved. But in our case, since we want to build a binary classifier, we will just restrict the number of classes to 2 instead of the 3 classes of flowers that you would actually want to classify using this data set. We'll just take iris setosa and we'll split our uh, data in a way that we only have, let's say, 50 samples which are iris setosa and 50 samples which are not. So that's what we are going to build, and the model that we'll use is logistic regression, which natively is a binary classification algorithms. It can be extended to be used as a multi-class classifier, but in this case we'll be using it for binary classification. So that said, these are the prerequisites that you have to keep in mind to go to follow along for this series. The first one is obviously the programming language that we'll be using, that's Python, and I guess any version above 3.6 would do, above 3 would do. And our execution environment will be Jupyter notebooks, which I find very convenient to in demonstrating things. And for this part 1, which is the part we are on right now, the theoretical part would include these things. So these are super important, and I'm assuming that this stuff is usually from high school maths, so that shouldn't be an issue. And a wee bit of calculus. Here we'll use partial derivatives, and if you don't know what they are, I guess these symbols should remind you what they are. If you have ever come across partials, this is what they look like. We would be talking about this too, so you don't have to worry if you're not really sure about what these things are. They are pretty simple. And linear regression fundamentals, this part is for those who are coming to logistic regression after linear regression, which is usually what people do. So even if you don't know what linear regression is, or even what regression is in the first place, stick around. You will have an idea of what that is. And finally, there should be a zeal to learn, obviously. So let's start. So this will start with a goal-based approach, right? So our task is to build a binary classifier. So we're building something. This is the something that we're building. Let's call it B, which will take in some inputs and it will spit out an output. That's what you are building. Simplest way possible to explain what we are building would be this. In our case, it's a binary classification task, which what that means is our output would always be either one of two classes. Of course, it's a discrete output. So a discrete output means that the outputs are like, I don't know, they can be 0, 1, 2. They can be one example from a set of many examples possible. And in the other case, you can have continuous outputs too, which is not the case here. A continuous output is any real number, which usually is denoted as this. This notation is used for real numbers, which means it can be anything from -1 to, I don't know, 5.5. It can be 3, I don't know, 31. But in this case, we are just concerned with these kind of outputs, where the output can be one out of several classes. And more specifically, it is a binary classification task. So output 0, we will set the data set would be set up in such a way that 0 should mean that your input was not iris setosa flower. It wasn't the iris setosa species. And if it's 1, it means it's iris setosa species. So yeah, that's the case. And this is our data set. This is the thing that we'll be working with. So as I mentioned in the previous slide, you have x1, y1, x2, y2. So this x1 actually is a four-dimensional vector. And for those of you who don't know what vectors are, it's basically a bunch of numbers. That's your vector. And it can have a lot of interpretations, but in our context or in our use case, these four numbers here, petal length, petal width, sepal length, sepal width, this is one vector. And this is how you'll have your data set also. Your data set will be just these files or whatever, and they will be in this format. So our inputs are basically every individual input from the data set consists of a label and this vector. So again, to go back to this, our x1 is this first row up till here is x1 without the label. Obviously we don't need this part for x1, and so y, in this case y1 is 0. So y1 is 0 and x1 is 5.1 comma it's basically this, it's 5.1, it's comma 3.5, and this vector. And this simply means that we are not dealing with this flower as a picture or as an image with pixels and everything. We are abstracting this whole thing down to four numbers. So that's very important. The knowledge that we have about this system or this environment or this object is just these four numbers. That's all we know in our system, nothing else. We just know what the sepal length is, sepal width is, petal length, and petal width is. And based on that information, we have to predict which flower this one is, this sample belongs to. So yeah, this is just reiterating what I just said, that if this was a computer vision problem or something related to image um, classification, then we would probably be dealing with inputs that are very different. So, but in our case, we just have four features requisite. So if you already know this, that's pretty awesome. It's good for you. It would help you. But even if you don't know, linear regression basically, let's forget the word linear for now. Just regression basically means that if you're given two variables that you have dependent and the independent one, and they have some kind of a there's a linear dependence, let's say, that is visible. You can see that there can be a straight line fitted to this kind of a data set. Then when we talk about regression, what we are saying is that if I have these points, these blue dots, give me a straight line which fits almost perfectly with these dots. And of course, there's a metric that we use to answer the question that what is a good fit. And if you're wondering that how do I even use this thing? Well, if you already know about the values of umbrellas sold, when the rainfall is, let's say, 90 mm or something less than 90 mm that we can see here, and you know about what happens when rainfall is around 120 mm, it's something between 40 to 50 umbrellas. The thing here that linear regression does is that it helps you answer the question, what if there's a new value in the future which I don't of which, or sorry, for which I don't know how many umbrellas would be sold. Let's say somewhere around here, or even here, let's say in my data set I don't have any values where if 150 mm of rain happens, then how many umbrellas would be sold. Now that's a prediction, obviously this hasn't happened yet, but hypothetically if that happens, what will be the output? So what regression does for you is that it gives you this function. This is a model or a function which is actually a straight line function, but that's not important right now. And it tells you that, hey, based on all the data that you gave me, which is these blue points, I have actually made a function for you which will help you know that for an unseen example in the future, xi, what should be the predicted output, which let's just call it y hat I. And that's what regression is. And this is actually pretty staple for any supervised learning problem. Again, if you don't know what supervised learning is, it simply means that you need a bunch of vectors and labels, and at the end you want to find a function that can map those inputs to those labels with some metrics involved that actually tell you how good or bad this function is. So how do we go about doing that? Well, every function has to have some tweakable uh, parameters. So in this case, these are tweakable parameters. So if you know about your straight line, y equal to mx plus c, so 0 and theta 1, this is the Greek letter theta. And so this kind of a equation, which is very similar to the y equal to mx plus c, actually it's the same thing. The c is theta 0 and m is theta 1. This will give you a straight line. So the thing to note here is that when you have more than, let's say, when you have three um, parameters, so the geometric interpretation would be different, obviously. Then you'll probably have something like a plane, you know, a plane. This is the best I could come up with. This is a plane. So for a plane, you'll probably, when you have theta 0, theta 1, and actually there's a typo here, this should be theta 2. So that will give you a plane. So that essentially means you have three parameters and you have two independent variables. So let's say you have theta 1 plus theta 0 plus theta 1 x1, and you have theta 2 x2. And there's a term for this, it's called a hyperplane, which simply means that, let's say in this case, you have two-dimensional inputs, right? I mean, you are on a two-dimensional plane. This is a two-dimensional thing, right? This is a plane itself. So for that, the hyperplane is a one-dimensional thing. Now, one-dimensional obviously means a line. Straight line is a 1D thing. If your inputs were in a three-dimensional space, let's say somewhere here, which makes sense because every set of inputs x1 and x2, you are getting an output y1. So in this case, the hyperplane would be a two-dimensional thing, and that two-dimensional thing is this is the equation for that two-dimensional thing. So this is your model that we begin with. We need to have something, right? We can't just guess what the function will be, and it usually helps to have some domain knowledge in this case. For example, we know that this has to be a straight line model. Of course, if our data set looked something different, let's say if it looked like this, let's say the points that we had were like so, here. So this is definitely not going to be modeled by a straight line model. It's impossible. You can't have any straight lines that will give you a good model for this. It will be something like this or whatever. So you get the point. So that's our first step, that we need to pick something, right? We need to pick a model. In this case, it's linear, but usually in supervised learning, we start with something, be it regression or classification. Then we need to see the cost. Obviously, this is a guess. You can consider this as a guess, and the H actually stands for hypothesis. So it is a guess. This H is hypothesis here. So we have to check the cost, and then we tweak the parameters. We change this thing. We change theta 0, theta 1 up till, this is a typo, this should be theta 2, this should be theta n. So we change all the theta. So if you consider theta as just a vector, of parameters, you started from theta 0 and you go up till theta n. Okay, so you have n plus 1 things to be tweaked here. And then obviously after tweaking, since h or our hypothesis is a function of thetas, all thetas, so that will also change. So you tweak them and the h changes, and then you repeat until you're satisfied with the error percentage. So this is important. So we essentially, what we do is we start with something that's very crappy. We start with a crappy model which will not give you good answers. So in this case, we could have started here, right? Let's see, this would be our first line. And then, it gets better. Then we go here, and then we have something like this, and then we have this. And for each and every one of these linear models, there is a cost associated. The cost, I'll come to that later. The cost essentially tells you how bad it is, right? So we start from a crappy model, and then we go to a less crappy model. And then after, 10, 15 iterations, whatever, when we are satisfied the amount of how bad the model is with the error percentage, then we stop this process. Needless to say, this is an iterative process. This has to go on and on again and again. So cost essentially in this case is, if I had to ask you that, how do you know, how do you judge the um, how do you judge whether this model is a good one or not? Is it a good model or is it a bad model? So in this case, in this specific case of regression, where essentially you just need to predict uh, a real number, I would probably say that, well, if my actual output was 10 and it predicted 9.3, where my actual model was, my actual output was 100, but it predicted 1. So this is pretty clear that this is a very bad model, because the error here is like it's off by 99. This is off by 3 and this is off by 1. So in terms of the absolute differences, this is the best model, and then this is the second, and this is the worst one, right? So this was done for one example. So to get to get a brief idea, or to get an idea, excuse me, to get an idea of how good or bad your model is, I can do the same process again and again for each and every sample. For each and every data point, what I do is, for each and every one of my things in the data set, for every input, I'll pass it through the model, which is this. This is the function that we predicted. The model, let's say the h that we were talking about in the previous slide. And what I do is I subtract the actual value from it and I square it. And the reason for squaring the difference is that it will, in the later part here, when we are actually tweaking in this part, the step 3, this comes handy. I mean, the worst models would perform way bad if we have a squared function rather than a simple absolute difference, right? So that way, that's a good way to think about it. That's what we do, and this cost function is used in linear regression usually. So m is the number of examples here. This is the average operation actually. And again, the reason for keeping the 2 here, I guess, is because in the later parts, when you actually use partial differentiation on this equation, this 2 actually comes out, and this 2 and this 2 cancel out each other, and it's convenient. But yeah, so this is what linear regression is. I mean, it's tempting to think that we could actually use this exact same procedure for not only continuous output but for discrete outputs. What I mean by that is, pictorially, here's an example of the same. So let's say these are the inputs, right? These are the x's and the y's. These are the x's, sorry, the age. This is the input vector. And obviously y in this case has to be 0 or 1. So based on the age, we are determining whether a certain product P, let's say, would be purchased or not. So let's say there's a 20-year-old inside a sample who had not purchased the product, and hence the output for this is 0. And there's somebody with the age somewhere between 12 and 15, let's say 13, who had purchased the product, this one. So that's 1. So first we use linear regression for this, and we just we fit this straight line to this expression. And now what we do is we make a simple thresholding rule, not purchased, right? On the other hand, if it's greater than 0.5, if the output of linear regression is greater than 0.5, then we'll say that you are going to purchase this, right? So this is what thresholding is all about. It's a very simple thing, and intuitively it should make sense why this might work. Now the problem is, okay, the first problem obviously is that if you notice here, as we start around 26, the values are being negative here. Now for classification algorithm, a negative value does not mean anything. It's very hard to interpret that as anything. And the other problem with this is it is sensitive to imbalanced data. So up till here it's okay, but if we had more points after, let's say in this age group from 60 to 70, then you can clearly see that it is misclassifying examples if with the thresholding logic. So this is the 0.5 again. Okay, so you can clearly see that this is the 0.5 line. This is where you have y equal to 0.5 in this line. So these values, let's say this value, for example, at 20, according to our hypothesis, is this. Now this is greater than 0.5, right? So this input on our hypothesis gives the prediction of greater than 0.5 according to the linear regression model. So that would mean that this person does purchase, right, based on the simple thresholding logic. So then accordingly, this at 20, so we'll say when x is equal to 20, so our y is equal to 1, or y hat, which means the predicted output is equal to 1, which is obviously a misclassification because all these are at 0. These are the not purchased ones, and yet this gives the output that it will be purchased, which is wrong. So the two things that we know for sure now is that we need the discrete values. We don't need continuous values. And secondly, our model should be able to handle imbalances in data. So that's why, it's not really good for classification tasks. So what do we need then? What do we need? We need something that, we have established the foundation for our model, right? But the problem is that the output that linear regression is giving can be anything from minus infinity to plus infinity. It's just like it's a linear model, right? And a linear model is what? It's a line basically. So a line's domain, a line's range, it can be anything from positive infinity to negative infinity, which is what we don't want. We want something between 0 and 1. And this 0 and 1 is important because we are actually going to be predicting the probabilities here, and I'll talk about that in a bit. But for now, let's just think about this. Do we have anything that can give us 0 and 1? Something between 0 and 1 for all values of x? Well, actually it turns out that there is something which we do have, which will do this thing. And that's your logistic or the sigmoid function. Now just take this in for a second and you'll observe that for any positive value, these are the positives on the x-axis, right? This is between 0.5 and 1. And for any negative value, this is somewhere between 0.5 and 0. And also observe that this function has this peculiar property that as you go towards very large positive numbers, which mathematically this means a very large number, which is like greater than 0, any x, it approaches 1. Similarly, for a very negative number, by that I mean a number like, I don't know, minus 10,000, minus 10 million or whatever, they will approach 0. So these are the two properties that we know of this function. So we can use this probably in our case because regardless of the input, whether it's from minus infinity to plus infinity, let's just write that down. The domain of our inputs is minus infinity to plus infinity, and yet the outputs will always be somewhere between 0 and 1. I'm not actually including 0 and 1 in that because they never actually reach 0, and you can actually see why that happens. E is very large, then 1 divided by e raised to t will be very small, and if 1 divided by e raised to t will be very small, then this thing will essentially become 0. And if this becomes 0, then the denominator will essentially become 1, and if the denominator becomes 1, this entire expression will be close to 1, which is why at very large values, positive values of t, we approach 1. Similarly, if t is highly negative, then of course in this expression here, this becomes a minus t, right? So to give you an example, if we have e raised to minus 50 is simply plus 50. It's e raised to 50, and this is a very big number. So we have essentially 1 plus a very big number. So that means this entire expression would be approaching 0. Okay, so we have our final product now. For each input instance inside our data set, this is what we'll be doing. We'll be predicting the probability that that instance belongs to the positive class. And to put it in a different way, what we are saying is that let's say for a particular instance, if I had 1, 2, 3, 4. This is petal length, petal width, sepal length, sepal width, and I pass it through the model that we built, and it gives me the value 0.9. So the question is, what the heck does this mean, right? What is a 0.9? Well, a 0.9 is the probability that this input sample, this example, belongs to the iris setosa class in our binary classifier. I mentioned there that binary classifier built using logistic regression, which is important, the LR model. So there are basically 4 things that we need. We need a hypothesis function, a model, that is. We need a squishy function, which is the sigmoid function, and we need a cost function. I haven't talked about the cost function in the case of classification, so stick around for that. That would be interesting. And last but not least, we need a function that will update, to remind you of the tweaking thing. In the linear regression case, we had to update these weights, right? Theta 0, theta 1, theta 2, and theta n. So we need a function for that as well. So there's a lot of questions as to how do we update them, how do we know when to stop means. So let's say we have a problem where we're supposed to predict the price of a house, and the only information that we have from the historical data is the number of bedrooms and bathrooms. So you can look at it in this way, that these are the vectors. So x1 is 2 3, x0 is 2 3, and x1 is 4 8. So you have the first house where the number of bedrooms are 2, and this is the number of bedrooms, BE, let's say, and BA, number of bathrooms. So based on that, if we have this linear model, what we do is we just we multiply them with the parameters. So in this case, the parameter vector thetas is this. So this is simple multiplication, which is also called weighted multiplication, by the way, because they can be considered as weights. That's a different notation, but essentially they are just the parameter vectors. That's all they are. And the squishy function, obviously. And this is an example where I have actually coded the thing here. So you can easily observe that 9, 8, it is very close to 1. And if you remember the graph again, this was expected because any positive value, greater than like 4 or 5, will make your sigmoid approach 1. The third thing is cost function. Now, in the case of linear regression, we were predicting continuous values, which it is. Okay, so the thing about the cost function is we have to first ask ourselves that what is the cost function doing here? And what the cost function is doing is it's giving us one single number, single metric that will tell us how good or bad our hypothesis is. So again, to refresh your memory, the hypothesis that we have, let's consider it's just this function f. Whenever it spits out any value, number 1, the value will be between 0 and 1, and it has to be interpreted in this case as a probability that the input vector for that sample is belonging to the positive class. Now in our case, the positive class is iris setosa, but it can be anything. In let's say a cancer classification problem, this could mean cancerous, right? Or it could be a spam classifier and it could mean spam. So this is the positive class. But this output that the model gives you is a probability. So the cost function, which is a good one, should have a very high value if let's say we have an example where y should be equal to 1, true value, but our model actually gives us a very small probability for that example, right? So that means it's incorrect. So we need to penalize that instance, and that's why the cost should be very high. On the other hand, if the true value is 1 and the probability given out by our hypothesis is 0.9, this means that according to our model, the probability that the input vector x, the sample that we just were working on, belongs to the positive class is 99%, then the cost should be low because this is what we wanted and this is what we got. So the gist is, if the predicted is close to the actual value, your cost should be low. So an example again for this is that if this was actually an iris setosa example, meaning the true label is y equal to 1, and our model, which again spits out a probability of belonging to the positive class, is 0.99, it's basically saying that I'm 99% confident that this is from the iris setosa species, which is actually correct, and so the cost should be very low. When the expected output, let's break it down into two cases. There's a case when the expected output is y equal to 1, which means it is an iris setosa species flower and not iris setosa. So let's stick with the is iris setosa case. So this function, logarithmic function, if the value inside this is, is very close to 1, let's say, this should spit out a very small value, right? Or if it is close to 0, it should spit out a very high value. That's what we want. So does this function help us or not? Let's see. So this is a case of y equal to 1. Now let's pick up any random point. Okay, let's take 0.9 first. This seems like 0.9. Now this means that we have predicted that the input is 99% iris setosa when actually it is iris setosa. So that means the cost should be very low. Well, that's what we have here. The cost is very low. Good, that's good for us. And this is the case when it was y equal to 1. It should be iris setosa, right? But what we have predicted is that there's only a 10% chance that it is iris setosa. Again, that's not good. So the cost should be high. Well, the cost is high. On the contrary, so in this case, the probability of being positive is 10%, obviously. So that's why, that means the probability of being the other class automatically is 90%. So since we are confident enough that this is not the iris setosa class, but the other one, which is not iris setosa, y equal to 0, then we have a very low cost because we are on the right track. Makes sense? So these two things can be combined and you can actually test it out. You can, if our y equal to 1, right? And let's say our hypothesis gives us 0.9. So what will happen? For that particular example, what we'll have is this part firstly becomes 0 itself. It cancels out. Now we deal with this part. So y equal to 1, and then we have to take the log of this value, which again, if you go back to the graph, would be somewhere around here because it's 0.99. It's very close to yeah, oh sorry, it's here, my bad. 0.99 is here, so the cost should be low, which is exactly what we wanted. In the other case where we have the negative class, so y is equal to 0. Okay, so this cancels out and now we are left with this. So essentially what we do is 1 times logarithm of 1 minus, let's say we predicted there's a 10% chance, 0.1, that this belongs to this class. Okay, sorry, there's a 0.9% chance that our current input x belongs to this class. So 1 minus 0.9 would be around 0.1. So again, we can see that at 0.1 here, the input, the cost is very low, which is as it should be because the probability of our input vector belonging to the negative class is 90% in the case when it should actually give the output of negative class. So we are on the right track. We mean that for every input instance in our data set, we'll multiply the ground truth value, which is this y superscript I, with the log of our predicted hypothesis value, which again, just to remind you, this hypothesis was the weighted sum of all the inputs. And that sum itself had to pass through the sigmoid function, which was this. So if this is z or z, then this is our output. And this output is the one that we are talking about. And essentially we do this for all the samples, and we divide it by m because it's an average cost. And yeah, that's it. And there's a negative sign because because at the end we need a positive value for cost, and inside there will be negative, so that cancels out and we have a positive cost. Now now we have the cost function, right? So we are almost through. We know how bad the model is, but how do we improve the model? Because this wouldn't be called machine learning if there's no improvement with data. So how do we find the right set of parameters? So essentially our goal in this case is, for this expression, the one that we started with, we need to find the thetas such that our cost is as minimum. Our cost is minimum. So in simpler terms, let's just look at a, I don't know, quadratic cost function. Our cost function is not as simple as this one, but this pretty much sums up the idea of what I'm trying to explain now. So let's say we are doing a machine learning problem, and for that problem, this was our cost function. All right. So our goal, as I stated before, is that we need to find the thetas such that the cost is minimum. That translates to, we need to find the value of x where f of x is minimum, right? So again, in simple terms, this means that we need to find the minimum value of f of x, or in other terms, this means that we need to find the argument x that gives us the minimum value of f of x. And in our case, that x is actually the thetas. So we had a cost function which was a function of these thetas, which was a function of these thetas. And we need to find those set of thetas for which the cost function is minimum. That's our goal. So in this case, what we usually do is, in such optimization problems, we usually look for the slope of the graph, at least in these quadratic cases. So just to remind you of this simple calculus trick is that whenever you're looking for a minimum or a maximum, the slope there is 0. And you can see that here, like this is the slope, right? There is some slope here, there's slope here, but at this topmost point, this point, slope is always 0. Here we have some slope, here we have some slope, but at this point, the lowest point, the slope is 0. So the simplest way to find out the minimum is to just equate that slope equation, because that's what the slope equation is, right? Slope equation for this is 2x plus 2, and we just equate that to 0 and we find out the x. Now this x is where you get the minimum of this function. So you can actually test it out. You can see that at -1 the value would be -1 squared, which is 1, plus 2 into -1, which is -2, which is -1. So I know probably the thought that 0 would be the minimum here would have crossed your mind, but actually the minimum or the smallest value that this function will ever attain is -1. Just as a fun trick, if you want to find the maximum of this function, well, the maximum is infinity, because there's a defined minimum, but there's no maximum, so that's not an issue. So we did that here pretty easily, right? But we can't always do this because of computational issues, and because sometimes this just does not exist for certain functions, for the complex functions. So what we do is we do an iterative approach, which is called gradient descent in this case. So the iterative approach simply is, rather than just taking a closed form equation and just solving for it, what we do is we start at some point some random point, and we try to get to this point, which is the minimum, which is what we want. And the way we do it is, at every point we compute the slope, and this step, the third step. So let's say this is a graph, this is our cost function. So we were here, we compute the slope, right? And then what we do is that we update the value of x, it's like so. And this LR is something called learning rate, which actually scales as to how fast you want to go down the hill. So this is an example of the same, because it would be better to work with an example. In this case, let's just see, we started at x equal to 10. Let's say we were here, x equal to 10, and x equal to 10 is 120. We have some value, and so this is -1, and this is our function, right? So at -1 we get -1. I know this isn't a perfect curve, but stay with me for a while. This is -1. Now at x equal to 10 we had 120, and we had a slope value. What we do is, to update that x, we replace it with x minus LR into the differential. So that gives us a new x, 7. The learning rate, obviously, you can see what would happen if we did not have a learning rate. So then it would update itself like 10 minus, if there was nothing here, or if learning rate was like very high, let's say it was 1, so it would be 10 minus 1 into this 22. So you can see what this would do, right? This would so the x, we actually need to be here, or in terms of the x we need to be here, but this would directly transport us there, which is not what we want. So we have to be very slow here, and that slow, that reduction in speed is accomplished by the learning rate. Now you can obviously tweak it, you can keep it dynamic and all that, but this is the simplest case where you just have a constant value of 0.1. So what 0.1 does is, we have 10 minus the learning rate into the differential, which is this 22. So this is what this is 10 minus 2.2, and if you do that you get 7.8. So we keep doing that, and you can see that the x keeps reducing, and we are getting towards the -1. I want you to remember that our expected answer should be -1. Just because we change the procedure, this should not change. We should still get to -1, right? Yep. So you see, we have actually reached -1 around this point, around here. You can see that fx also becomes -1, and the slope is almost 0. And this is your gradient descent. In a nutshell, what we're doing is, we are using the slope to guide us towards the minimum. Now that we know what gradient descent algorithm is and the steps involved, the next question is, how do we use that information now to actually be applied in our case? See, the example that I showed here for illustrative purposes was a very simple example, and realistically you will never have a cost function which is this simple. So also, the other thing that you should have noticed by now is that in our case, in our hypotheses, we don't have one variable or one parameter that we have to tweak, right? Our function is composed of, or we get our function, we get our hypothesis value at least before we do the sigmoid. This weighted sum has more than one independent variable. See, more than one parameters. You have θ0, θ1, θ2, and θ3, and we have 4 features: sepal length, sepal width, petal length, petal width. So compare this equation, this expression, with the one that we worked on. So the first thing that is pretty obvious is that here we only have one variable, and there's x everywhere in the expression, so that's why it is f of x. But in our case, the correct way to write this h would be h of theta 0 and theta 1 and so on till theta 4. So the interesting question here is, what do we do when we need to do something similar to what we did here, computing the slope and all that, when we have more than one variable? Well, what we could do is we could just change one variable and keep the others as it is. And what I mean by that is, essentially the question that we were asking ourselves is, how much do I change one parameter? Again, in this case, we just have one parameter, which is x itself. So we were asking that how much do we change this? Or, sorry, to put it in a different way, what would my change in x give me? How much would that affect the function, right? And similarly, in this case, this example, if you plot this would be in 5 dimensions, which obviously you can't visualize. But for a simpler case, if you just had theta 0 and theta 1, let's say, you had two parameters. So the cost function for this would be something like this. It would be something in this 3D space. I'm not sure what the shape would be. It can be this or something else. But the point is, so what we will do here is that we will use this thing. We will use this one parameter and keep all the others as constant. So let's say we want to see how much will the function change, will the cost function change if I change just the theta 0. Or to put it in different words, if I change the value of theta 0 by a little bit, how much will my function change? And you have to remember that all the other things here are constant at this point. They are treated as constants. So yeah, that's what partial derivatives are. So when we have a 2D plane, sorry, I'll go back. See, in this case, when we have a 2D plane, your slope can only have one direction, right? I mean, no matter what I draw here, the slope can only have one direction, right? So it won't mean anything if I say a slope in x, a slope in z direction or y direction or whatever. The slope has only one direction. So, and so it's pretty obvious that there can only be one kind of a slope for this case. But here you can have a slope in x, a slope in y, and again what that means is you are making that little change in x or y. That's your partial derivatives. Now how do we use this? Well, we use this in this way. We compute the partial derivative for each and every parameter, right? You have to keep in your head, you have to keep that x squared plus 2x example in your head, just like we had df by dx for that example. That's the same thing here, but this is like for each and every theta, right? So this basically tells you that if I change theta j by this little bit, this will be the effect that it has on the function. And now, as it states here, that in simple English, this thing is the average of the error, which is this. And remember that this is the sigmoid function. So this is this 1 plus 1 raised 1 plus 1 divided 1 plus 1 raised to e raised to this thing. The weighted sum, theta 0 plus theta 1, that thing, right? And we subtract this. That's why we're calling it the error, because it's the difference between the true value and this predicted probability. And we multiply it by the so this notation here simply means that, so in this slide, if x1 is equal to 5.1, 3.5, and then 0.2, the first row, this is x1, then the first value in this vector x1 1. So superscript usually means that we're talking about the entire vector, and when I subscript on a superscript, this index tells you which value inside the vector, the first value, second value, third value, so on and so forth. Okay, this is essentially what this is, the same thing. This we know what it means. This superscript is the entire vector, and this has a subscript, which means that if we are dealing with theta 0, then let's say we have these features here, x0, x1, x2, right? 1, 2, 3. So we'll compute this thing and we'll multiply that with 1. If you're dealing with theta 1, we'll multiply that with 2. So you get the point. This index of theta and this should be the same. This is again the entire vector, the features, the 4 features, that's what it means. So yeah, that's what we do here. And the thing about theta 0 is, actually I don't need to go there. So for a weighted sum, usually we don't have any theta 0 feature, right? We only have features from x1. So in our case we have 4 features, but since we have theta 0 here, we need a 5th feature. So what we do is, if this is our data set, these are the 4 features, right? This, like so, we just add another feature here, which is all ones. Now you can call this x0. X0 is always 1, so that's why you have this thing, this. But this is only for theta 0. So that means that your partial derivative with respect to theta 0 is this. It's a very simple thing. It's just like, it's the sum of the errors. And so yeah, this is pretty much it. You can ignore this. This is just 1. And so first, what do? Let's recapitulate here. First, we needed a model. As I talked about, our first ingredient, we decided to go with this model. Then we need a way to squishy squash this thing when we went to the sigmoid model. So this can give you some weird large values like, I don't know, 9, 4. And then you have values like 0.99 and then 0.8. And then the interpretation here obviously is the predicted probability, right? Actually, this thing was the output coming from here, and we passed it to the sigmoid. Now we have something on our hands. We have, okay, I forgot to mention one important detail here, which is not really that great, but it should be obvious that based on this predicted probability, if you needed to give an answer like 0 or 1, you know, a predicted label, then if it's greater than 0.5, this, the output of this, the predicted probability, then you should just say that then the output should be 1. Okay, that's a bad color. This one works. It should be 1, otherwise it should be 0. It is quite obvious, right? Probability greater than equal to 0.5. After this, you just set the label, the predicted label, as 1, else you set it as 0. And then we do the cost here. Okay, for the cost we have this, which is the true label, and this, which is the same thing. Actually, this might confuse you a bit. This is the same. This is the predicted probability, by the way. And yeah, then you have the gradient. Let's put all the bits and pieces together now. This 5-step process is the iterative process that we'll use to train our model. The process of going through loops and loops of doing these 5 steps is what is called training, and this essentially is the learning part here, where your model learns, so to speak. So how does it do it? Well, it will use all the ingredients that we talked about. The first one is obviously the hypothesis being used here. So this was one of our ingredients, the first one. This is the hypothesis. We need these for the hypothesis. So these are randomly initialized, excuse me. Then we calculate the cost, which uses the logarithms that were used there. We can call it j of theta as before. Then we have the gradients, which we just talked about, delta j,
by delta theta for each of the parameters. Then we do the update step. This is exactly the same as we had in linear regression, but the only difference is that there we had just one variable, which is f of x. One thing was being updated, which is why you didn't see the partials, but that was the normal derivative that you see back then, df by dx. So once we do all this, right, we check for accuracy, and accuracy essentially is actually it's not compulsory to have accuracy. You can have a bunch of other metrics to test as well, but essentially we have something here. Let's just call that a metric m, which can be accuracy or which can be a bunch of other things. I won't go into that. And if that metric's value is satisfactory enough and you are happy with it, and so for example, if the accuracy is, let's say, 99% for your validation set, then probably you'll just move on and you'll save this model, which is essentially just a function. So yeah, that wraps it up. I hope you liked this video. And if you did not, then tell me why in the comments. And if you did, like, share, and subscribe. Thank you for watching. Stick around. There will be a part 2 where I'll be doing a code along for this. We'll build this entire thing, and I'm pretty sure that should be 1,000 times more fun than this video was. Thank you for watching.